Good afternoon, everyone. Thank you for joining us. We're really delighted to have you be here with us for this special Distinguished Lecture Series on AI. I'm Camille Crittenden. I'm Executive Director of CITRIS and the Bonato Institute, and I'm really pleased to welcome you here. We haven't had too many in-person events in this auditorium, so it's a real pleasure to see real faces and real bodies and have us all be here in the same space, so thank you. I want to welcome you again to the 4 distinguished lectures on the status and future of AI presented by the CITRIS Research Exchange and the Berkeley AI Research Lab, especially Ken Goldberg, who is also heavily involved in curating this series, so thanks, Ken. We've planned a remarkable lineup of speakers this month and are glad to see all of you here in person in Sutardja Hall here at UC Berkeley, as well as virtually via live stream today. So I encourage you, if you have friends who might enjoy the talk but weren't here, to have them check out the recorded remarks from today, as well as all 4 of the lecture series actually on the CITRIS YouTube channel. The next AI Distinguished Lecture will be held next Wednesday, April 19th from 12 to 1 here again in Sutardja Hall and live streamed again for a talk on how AI fails us and how economics can help with Michael Jordan, Distinguished Professor of Electrical Engineering and Computer Science and of Statistics here at UC Berkeley. Be sure to check the CITRIS events webpage for registration details and further updates. So we realize also that today we're really delighted that Sergey was able to step in when Alison Gopnik unfortunately came down with COVID and was unable to join us. We will reschedule her talk for the fall, so stay tuned for having her join us later on this year. We're honored to be part of a larger Berkeley AI series featuring 7 leading experts in the field, including the co-founder of ChatGPT, John Schulman. So you'll find out more about this when you visit berkeley.edu/AI. So check that out. We will have time for questions at the end of the talk. We have microphones here that will circulate afterwards, so please hang on to your questions and Sergey will address them at the end. We'll walk around so you can have a chance to ask your question. So today I'm honored to introduce Professor Sergey Levine. He received his BS and MS in computer science from Stanford in 2009 and a PhD also from Stanford in computer science in 2014. He joined the faculty of the Department of Electrical Engineering and Computer Science here at Berkeley in the fall of 2016. His work focuses on machine learning for decision-making and control with an emphasis on deep learning and reinforcement learning algorithms, which we'll hear more about today. Applications of his work include autonomous robots and vehicles, as well as applications in other decision-making domains. His research includes developing algorithms for end-to-end training of deep neural network policies that combine perception and control, scalable algorithms for inverse reinforcement learning, deep reinforcement learning algorithms, and more. So please join me in welcoming Professor Sergey Levine.
Thank you, and thank you very much for the introduction. I know some of you were looking forward to Alison's talk, so I won't be able to cover all the cool child psychology things, but hopefully I'll tell you about something entertaining, and there'll be some videos of robots as well. All right, let's. Can we get the slides? Okay, so let's start with a little thought exercise. Let's say that we'd like to design a robot that's going to go to another planet and explore that planet all on its own. No mission control, no human looking over its shoulder. The robot is just going to get dropped there. It has to, go putter around, explore this other planet, figure out whatever cool discoveries it can make there. And when it's done, it hops back on the rocket, flies back to Earth, and reports what it's found out. What kind of AI systems would we need to get this kind of thing to work? Not the mechanics of how do you build a Mars rover, I don't know anything about that, but in terms of the kind of reasoning the system will need. Of course, it'll need to be well prepared, in the same way that an astronaut kind of needs the right stuff, it needs to be trained, it needs to experience things maybe back on Earth about how to drive around on different terrain, how physics works, how the kind of basic common sense things. But it also needs to be resourceful, it needs to be able to deal with whatever unknown and unexpected eventuality might arise when it's on its mission. If something breaks, if it damages its wheel, if there's a malfunction, it needs to adapt to that. It needs to be able to respond to whatever unexpected things it might find on this planet. The whole point of going there is to discover the unexpected, so we need this flexibility and resourcefulness. In much the same way that a person stranded on a desert island, we need to figure out things, drawing on their past experience, but also learning new things and discovering new solutions to novel problems. We need both the ability to prepare in advance and the ability to flexibly adapt. So what has recent progress in AI provided us with that can help us tackle this kind of big problem? Of course, I'm not in the business of building robots to explore space, but I think that's kind of an interesting thought exercise to think about, and we'll keep that in mind as we progress through this talk. So let's think about kind of the big advances in AI that most of you probably know about from the past decade or so. Maybe we can group them into advances in data-driven AI, like the recent surge of generative AI techniques, as well as advances in reinforcement learning. And many of you probably have heard a lot about kind of the big milestones in these areas, but it's important to know that there's some pretty significant distinctions in how these techniques work. So the data-driven AI things, these are things like image classifiers, but also more recently models that generate images, models that generate text, question answering systems, of course ChatGPT and things like that. Reinforcement learning, that's things like algorithms that can control robots, play Atari games, and of course beat the world champion at Go. Both major AI milestones, both categories, but very different in some very significant ways that we'll need to understand if we are to think about how to build our Space Explorer robot. So let's start with the data-driven AI. What does that do? Well, of course, many of you know the kind of anecdotal examples. You can take, for example, Stable Diffusion, type in a prompt describing a picture of Salvador Dali who is half robot, and it will draw this thing for you. That's pretty cool. You can have a chatbot that will talk to you, answer questions, even do like coding tasks and things like that, explain jokes. But it goes further than that. Of course, you can build very practical systems like computer vision algorithms that will detect things in images. And you can even use these kinds of data-driven AI techniques for tasks, for example, in biotechnology. You can design proteins using this, in some ways, similar kinds of diffusion model concepts as what's been used to generate the pictures. So this is a video from the Institute for Protein Design at UW showing a diffusion model for a protein therapeutic. So how do these techniques work at a high level? I mean, obviously there's a lot of details, but at some very, very high level, the backbone of what makes these things work so well today is the ability to use very large data sets, often mined from the web, even for proteins they're actually mined from the web in many cases, in combination with very large models. And a lot of the advances that have fueled the really impressive things like this really come from figuring out how to make even bigger models and curate larger, more representative data sets. But at some deeper level, these techniques are based on maximum likelihood training, which means estimating the distribution in the data, either an unconditional distribution if you want a distribution over text that people would type on the internet, or a conditional distribution if you want something like an image classifier, or the distribution of pictures given a textual description. So we know about density estimation even from introductory statistics, kind of the boring low-dimensional version of this is like, okay, take a bunch of points, fit some PDF to them, and you get some curve. And that kind of doesn't seem very powerful. That seems like a statistics exercise. And perhaps one of the surprising things with the data-driven AI revolution is if you just scale this up enough, if you make the model enormous, not the three or four dimensions here, but billions of parameters, and the data set contains billions of data points, then you actually get stuff like this. But we could ask, what are these models actually learning? Well, they're using large data sets, typically scraped from the web. And because they're estimating the generative process that produced that data, what they're basically learning is how do people tend to produce data that they put on the web? If we're talking about pictures, what kind of pictures do people take? Or what kind of paintings do people draw? If we're talking about text, what kind of text do people type on keyboards? It might seem unsurprising in light of that when you interact, for example, with a large language model, it kind of talks to you in a way that resembles a person. It has that sort of flavor in its conversation that you'd associate with people. Why? Well, because it's trying to imitate people. It's trained on data, and its objective is to match the distribution that produced that data and that generative process is people typing on keyboards. So it makes a lot of sense that you'd expect these things to produce human-like results, although it is quite remarkable the scale at which that happens. Okay, now the trouble, of course, with this is that for our Space Explorer, simply reproducing the behavior of people is probably not going to be enough by itself. Like, when NASA trains an astronaut, they don't just like yank someone off the street and say, okay, you're going into space now. Like, that's not how it works. You have to actually prepare. You have to be better than the average person at that particular task. And you also need to learn, besides the background knowledge, the kind of resourcefulness and problem-solving skills that you would need to handle the unknown. You need to be able to not just handle diverse open-world settings, but you need to be able to come up with novel solutions to new problems that maybe were not anticipated during the training process. And reinforcement learning gives us a really powerful tool for this. But reinforcement learning is very different at some basic level to the techniques I discussed before, because reinforcement learning is not about estimating the distribution of the data. So what does reinforcement learning do? well, what is reinforcement learning to start with? Modern deep reinforcement learning actually draws on two branches of study, two very old lineages. The more obvious one, of course, is what is called reinforcement learning, actually originating in psychology with behaviorism and things like that, and its modern incarnation in algorithms that we use in computer science. But there's actually a second branch that's heavily influenced the modern study of deep reinforcement learning, which used to go under different names, things like evolutionary algorithms, large-scale optimization, that sort of thing, which dealt much more with the problem of coming up with emergent solutions to novel problems. This is a video from Carl Sims from 1994 that shows, in this case, not a reinforcement learning algorithm, but actually an evolutionary algorithm, coming up with emergent gates for these kind of fictional creatures. In this case, actually, the creatures themselves are also optimized, their body plans, but also their behaviors. And this is interesting. We look at this and okay, it's kind of cool. It's discovering swimming gates, walking gates. Fast forward 2 decades, and a very different type of algorithmic framework based more on optimal control, but applied in kind of a similar style with large-scale simulation, can discover much more complex behaviors with maybe more elaborate body plans, like this humanoid learning to stand up and walk. Now, these things are based on very different principles from the data-driven AI techniques I discussed before. Whereas the data-driven AI stuff is based on looking at lots of data produced by humans and figuring out what do natural pictures look like, how do you recognize things in images, how do you generate text. This is based on using optimization and simulation. This is all about discovering emergent behaviors with fairly concise high-level objectives like move forward, reach a destination, and so forth. So modern deep reinforcement learning really draws on both of these threads in the sense that the algorithmic foundations are very heavily inspired by the study of animal learning and human learning from psychology, but in combination with the large-scale optimization and simulation ideas that in some sense are derived from the stuff down here. And the basic recipe in deep reinforcement learning algorithms is, of course, that you have an agent. It interacts with its environment, uses that interaction to get a little bit of data, improve its behavior, throw out that experience, collect more experience with a new policy, and repeat. And this kind of recipe, when scaled up sufficiently, can solve some really difficult problems. And of course, one of the examples that most of you are probably familiar with is AlphaGo, which works essentially on this principle. Now, the remarkable thing about these kinds of systems is that they can actually discover solutions that are different from what humans would have done. They're not relying on getting lots of human examples. They're relying on learning through interaction with the system. One of the most vivid examples of this is in the second game in the championship match between Lee Sedol and AlphaGo, there was this move 37, which was a move that AlphaGo made that human commentators at the time didn't really understand. They were like, okay, this is kind of a weird move. Like, it seemed like it was playing really well, and now it suddenly did this weird thing. Turns out the move was actually really brilliant and it allowed it to win the game, but it was not a move that expert human players would likely have made because it was so different from how people generally learn to play the game. Now, this is really impressive, and that is really impressive. But it's impressive for a very, very different reason. The language models, the image generations, they're impressive to us because they look like something a person might do. The solution here is impressive because no person would do it. It's impressive precisely because it's a novel solution that people didn't expect. And our space explorer is going to need to do both of these things. It's going to need to handle diverse real-world situations with the common sense that people bring to the table from their prior knowledge, but also with the ability to come up with these novel solutions when necessary. Okay, now, why is reinforcement learning alone not good enough? Like, it kind of seems like, okay, space exploration, robot going to another planet, everything sort of suggests it's really a control problem, decision-making problem. Reinforcement learning might be the ideal tool for that. Well, the trouble with reinforcement learning is that the way that classical online RL is used to solve these large-scale problems makes it actually quite tricky to apply to complex real-world environments. Reinforcement learning, as I mentioned before, involves an agent interacting with the world, collecting a little bit of experience, improving its policy, collecting more experience, and repeating this many, many times. And this works really well, for example, in Atari games where you can interact with a simulator a lot, with the game of Go, where you can play billions of Go games. It even works for robotic tasks in controlled environments where you can have the robot repeatedly interact with the same kind of scenario. But in the real world, there's a lot more complexity and diversity. The real world has physics, objects, wide open world environments, other agents, and so on. And there's a really big gap between the kinds of domains where classical reinforcement learning methods have been successful in the real world. It's not so much a gap of like task complexity in the sense that like Go is a pretty complex game. It's a gap of breadth and diversity. The game of Go is governed by a fairly concise set of rules, and the Go playing agent doesn't have to worry about what happens if like its opponent spills coffee on the Go board. Like that's sort of outside of the rules of the game. But of course, the whole point of the Space Explorer thought exercise is that we don't know the boundaries of the game. When it goes to this other planet, all sorts of things might happen. So we're much more in that setting on the right than over here. And the way, of course, that the data-driven AI methods deal with this is they use lots of data from the real world to learn about the breadth and diversity that they might experience. So where does that leave us? We've got these data-driven things. They're great at capturing the distribution in the real data. They're great at learning about the real world. But they don't make purposeful, goal-directed decisions. They're not trying to really optimize some objective, and they're not trying to find novel solutions. They're trying to emulate humans, and they're actually very good at that. And we've got this reinforcement learning stuff, which is goal-directed and purposeful, but it doesn't make use of real-world data, and it's really just all about trying to optimize for a task. Now, at this point, some folks might say, well, okay, like this data-driven thing, it's going really well. Like, what's the problem? Just like do more of this, and maybe if you keep doing this, eventually the red thing will kind of go away. I'm actually very sympathetic to that view, but I want to tell you about a particular kind of perspective on this. This was actually put forward by Richard Sutton, who is actually, in some ways, one of the founders of the field of reinforcement learning in computer science. The stuff originated in psychology, but he was sort of one of the first people that really brought this to CS. And he wrote this wonderful essay about 4 years back called The Bitter Lesson. Many people took this essay to mean, like, we should do the data-driven stuff and basically nothing else. And like I said, I'm actually kind of sympathetic to that viewpoint. But I think that essay is also often misunderstood. So I want to give you a quote from this and discuss it a little bit. Here's the quote. We have to learn the bitter lesson that building in how we think does not work in the long run. What does that mean? Well, it means that if you want to build intelligent machines, maybe you shouldn't worry about, well, how is it that people think and really program in, like, oh, if you see, a tiger, then run away. The two methods that seem to scale arbitrarily are learning and search. So what does that mean? Well, that means that, well, if you want effective AI systems, focus on getting learning and search right, and don't worry so much about programming in your prior beliefs about how common sense reasoning should work. That's a controversial perspective. It's not something that everybody accepts, but it is something that has been hugely influential in one form or another on the modern study of data-driven AI. So some people take this to mean like, okay, that means that you just need to shovel more data into the GPU, right? Like, get out your shovel, find your big pile of data, and start getting it in there. The more data, the better. The bigger the model, the better, and eventually all problems will be solved. Not a crazy perspective if you think about the success of large language models especially, but if we look at this essay a little more carefully, notice that there's two things here, learning and search. There's two of those things that they're there for a reason, and they both matter. So learning, okay, we kind of know what that means, right? Use data to extract patterns. That's the good stuff. But what's this search thing all about? Well, Richard Sutton is a reinforcement learning researcher, and he used the word search in a very particular technical sense. Roughly speaking, search here means some kind of optimization procedure that you run where the more you optimize, the better you get at something. So search doesn't necessarily here mean like, A-star search, although that could be one form of search. But roughly speaking, it means using some kind of computation to extract inferences. And there's a big difference between learning and search here, because learning is about looking at stuff in the world and extracting patterns from it. So learning is really about looking at what's really out there in the world. Search is about analyzing what you found, typically through some sort of optimization process. So typically this would be some sort of iterative process that uses computation to make better, more rational decisions. And that could be search, as we learn about in introductory AI, like A-star search, or it could be optimal control, or it could be, of course, reinforcement learning. And I think we really do need both of those things, especially to build our Space Explorer robot. So learning would allow us to understand the world, get that common sense, that prior, and then search would allow us, would leverage that understanding for emergence, for coming up with novel, more effective solutions than the ones that we've seen, in the data on the web. So data without optimization doesn't allow us to solve new problems in new ways. Optimization without data is hard to apply to the real world outside of simulators. So we really need to figure out how to get both of those things. So can reinforcement learning, can these algorithms that do this optimization stuff, use data and optimization together? And that's really what this talk is about. The trouble is, out of the gate, reinforcement learning is actually two different things. And we're going to have to disentangle those things to get this right. Reinforcement learning gives us a framework for learning-based decision-making. And we like that because we want to do both learning and search. We want learning and decision-making. So it allows us to go from simply predicting the kinds of outputs we've seen in the data, predict the y's from the x's, to selecting actions based on states that are not necessarily the actions that match the data, but that lead to the outcomes that we want in a sequential process. So that's good. We want that. But reinforcement learning is also a framework, fundamentally, for active online learning for control. That's the picture from, actually, Richard Sutton's textbook. That's the picture from my slide. They mean the same thing. Iteratively interact with the world, collect some data, throw that data in the garbage when you're done, collect some more data, and repeat. And that's very hard to do at scale. If you want to generalize to the real world with data sets the size of like ImageNet, well, you're collecting ImageNet-sized data sets every iteration for thousands of iterations. Very hard to make that scalable. So almost all real-world decision-making problems basically look like that thing on the left. But almost all real-world learning problems also make it very difficult to get away with purely this online perspective. In the same way that the astronaut is not going to go to the planet and just rely entirely on online learning on the spot. They're going to come at the problem prepared with their prior knowledge. You don't want your agents to have to rely entirely on active online learning. So what we can do instead is we can develop offline data-driven reinforcement learning methods to basically get the best of both data-driven AI and RL. So instead of, so we want to try to get rid of the requirement for active online learning, but retain this nice formalism of decision making, which means that in contrast to on-policy RL, which interacts with the world a little bit, gets some data, uses the data to improve, and then throws it in the garbage, what we'd like to do is have a reinforcement learning framework that structurally looks a little bit more like data-driven RL, where we start with a large data set that was obtained from a variety of sources, maybe the agent's own past experience, maybe data that mined from the web, maybe examples that humans showed to it. Whatever that source of data is, take it and distill out the best possible behavior you can. Your Space Explorer robot should look at all of the experience provided to it and figure out, okay, based on this experience, these are good things to do when I'm in unfamiliar situations. And then, of course, when you're actually deployed, you can keep running online RL to improve from there. So if something actually changes, something deviates from what you've learned, then you can still adapt to it. Okay, so now we can think of a very basic kind of recipe to get us started for our Space Explorer robot. There's our robot. We have some data, and maybe that data comes from things the robot did here on Earth. Maybe it puttered around here on Earth exploring different kinds of Earth environments. Maybe it's data that people gave it. Maybe there's someone pretending to be an astronaut in Hawaii, and they live there for a year, and they provide the logs of what happened, and that the robot can use that. Maybe it's also other experience that is not obviously related to exploring another planet, but just kind of allows the robot to learn about physical events in the world, kind of what happens, cause and effect, various common sense knowledge. And we're going to take that, and that's going to be our data set for offline reinforcement learning, which will provide an initial policy for the robot so that it kind of understands how to deal with the physical world. And then it goes off to another planet. And when it's there on that other planet, it can keep running its RL process, it can keep improving and keep fine-tuning based on new things that happen, so that when an unexpected event takes place, it can actually synthesize what it learned with its new experience to discover, hopefully, a novel solution to a new problem. So that's what we're going to aim for. And the technical part of this talk will actually mostly deal with the offline stage, because in some ways this online part, that's kind of already decently well understood. So if we can get the offline part right, then that might open the door for a lot of these things. So I'll talk about the fundamentals of offline reinforcement learning. I'll talk about some applications of offline RL to robotics that we've done in my lab. I'll talk about recent work we've done for offline RL for large language models for human interaction, and then some work on offline RL for influencing humans in video game environments. And this will hopefully give you a few different perspectives on how offline RL can be used in combination with data to derive powerful behaviors from data that we might get from all sorts of sources. So let's start with the fundamentals. What do we expect offline RL methods to actually do? So one piece of intuition which people who are reasonably well versed in this area sometimes jump to is that, well, there's this other big thing in terms of data-driven learning of control, which a lot of people know about, which is imitation learning. So the first thing they jump to is like, okay, you're doing control with data, that means you're doing something like imitation learning. I think that's bad intuition, but there is some kernel of truth to it. So just to be clear what I mean by this, imitation learning, let's say you want to go from green to orange, you have some examples that basically do that, and you want to more or less copy those examples. Supervised learning can actually solve this problem to a degree. Oddly enough, there's some theoretical evidence that offline reinforcement learning can actually solve this problem better because it can reason about the dynamics in the scene. But I think that's not actually the main point. A better intuition is that offline RL is about getting order from chaos. It's about getting data that kind of goes all over the place and figuring out that if you combine this and this part of the data, then you can find a solution to the problem you want that's sort of supported under the experience that you've seen. I'll make this more concrete shortly. A very kind of obvious example of this, perhaps, is that, well, if you're doing some navigation thing and you've seen that you can go from A to B and you can go from B to C, you ought to be able to figure out that you can go from A to C. Okay, that's kind of basic. That's not maybe all that interesting. But now imagine scaling this up and doing this everywhere at once. Maybe you have lots of suboptimal behaviors. If you can figure out the best parts of each behavior in each place, then you can do much better overall. If you have data from lots of human drivers who are each very good in some situation but maybe bad in others, If you can get a machine that is as good as the best driver in every situation, then overall that machine will be much better than any one human. So it makes sense that this would actually be really powerful once it's scaled up enough, once it has enough patterns in diverse situations to draw on. Okay, so that's kind of the good news. Now, what's hard about offline RL? Like, why is this an actual field of study that we have to be concerned with? Well, the fundamental problem is that in order to perform offline reinforcement learning, you need to respond to counterfactual queries. So let's use that car example because, lots of us drive cars, so we kind of know how that works. Let's say that you have lots of data from human drivers. And let's say they're not like perfect drivers, but they're okay. Like, maybe it's in California, so we all kind of know how to drive, but we sometimes get creative, so maybe we won't stop at the stop sign every time. But we're not going to do like weird stuff like swerve off the road and go into a ditch just randomly. So when the policy is learning from this data, it needs to figure out, like, if I do swerve off the road and go into a ditch, is that good or bad? I mean, like, we know that it's bad because we kind of understand physics, we understand the world, but it's actually kind of hard to tell if all you've ever seen is halfway decent human driving. So online RL algorithms, they actually don't have to worry about this because online RL algorithms, they will swerve off the road and go into the ditch and discover that that's a bad idea, which is fine in simulation, but you really don't want a real car doing that. Offline RL methods need to somehow account for these unseen out-of-distribution actions, ideally in a safe way. So the obvious answer is like, don't do it, but you can't just not do anything because you still have to make use of generalization to come up with behaviors that are better than the best thing seen in the data. So now you have a really delicate balance to strike where you have to allow the thing to generalize, to discover new behaviors for which it can make correct inferences that that's a good idea, but not allow it to attempt to generalize to things for which it can't possibly know the outcome. So swerving off the road, don't do it because you don't know what will happen. But if you've seen people turn like this and turn like that, maybe you can kind of go somewhere in the middle, and that's a little bit better. So that's a delicate balance to strike, and it's not at all obvious how to design algorithms to do that. All right, I'm going to give you guys a quick primer, kind of a crash course on offline reinforcement learning. This is kind of the main part of the talk that has some technical content. It's not actually that critical to understand the rest of it, but I wanted to have like a little bit of a technical discussion. So first, a quick primer on off-policy RL. So off-policy RL is basically like offline RL, only you still collect the data iteratively. And that's what we're going to use as our foundation, and we'll build on it. So in reinforcement learning, an agent interacts with the world by selecting actions. We use A to denote actions. And the world responds with states S and rewards R. And the goal is to find a policy, which conventionally is described as a distribution over actions given states. And a good policy is one that maximizes the cumulative reward that the agent will receive over all time. So find a policy so that the total reward in expectation over the agent's lifetime will be large. A very useful object for doing that is something called the Q function. The Q function tells you if you start in a state S and you take an action A, and then you follow whatever your current policy is, what's the total reward you'll get? And the Q function is a very fundamental object if you want to derive reinforcement learning algorithms, because if you can get a Q function for a particular policy, you can find a new policy that is at least as good or better simply by being greedy with respect to your Q function. So figure out what is the Q value of different actions for your current policy, and then take the one with the largest value, and that'll get you a better policy. In fact, you can also short-circuit this, and you can directly solve for a Q function that satisfies what's called the Bellman optimality equation. Roughly speaking, the way you get this equation is you just plug in that argmax into the definition for the policy, write a recursive equation for the Q function, and you get this relationship. And what the Bellman optimality equation says is that if your Q function satisfies this, then its corresponding greedy policy is the optimal policy. And this is the foundation for a lot of RL algorithms, Q-learning, fit of Q iteration, actor critic, et cetera, which basically say, well, let's approximate the error in this equation, take the left-hand side minus the right-hand side, using some samples. So there are many algorithms based on this principle, but roughly speaking, what they all do is they take the left-hand side, subtract the right-hand side, minimize the difference using some sampled states and actions. If you can do this for all states and actions, you're done. But of course, in reality, the total number of states is uncountable, so you would use samples. And the cool thing about this basic idea is you don't actually need to assume that the samples come from your latest policy. They could, in theory, come from any policy as long as it covers the space well enough. So that gives us a really nice place to start if we want to think about offline RL algorithms. We could say, well, hey, if this is already a method that doesn't require data to come from any particular policy, let's take all the data we've got and just run this minimization, and maybe that'll work. And that's a good starting point. And for a very long time, people thought this would be good enough until we started doing it with neural nets, and we found out that it was actually a really bad idea. So why is it a bad idea? This is that same equation, just written in a slightly different form. Let's change it a little bit in a way that is mathematically equivalent, but reveals the problem. So instead of this max, I'm going to write this q as an expected value under some distribution pi nu. And pi nu is going to be that argmax. So pi nu is probability 1 assigned to the argmax, 0 to everything else. That doesn't change the equation because if you plug the argmax, you just get the max. So these are exactly the same. But this makes it more obvious that in order for this to work, you need to be able to get accurate estimates of the expected value of q under this pi nu distribution. And in machine learning, if you ever want to know whether you can get an accurate value of the expected value of some function, the first question you ask is, well, what distribution was it trained under? You can get accurate expectations for the same distribution as training, right? Test needs to match train. Well, it's trained under the data distribution. We call that pi beta for behavior policy. So whoever was behaving and producing the data, that's the behavior policy. So you minimize the error under this behavior policy, and then you test it under this pi nu. Okay? So you expect good accuracy when they match. But of course, they don't match, because the whole point is pi nu is supposed to be better. It's supposed to improve on the average in the data set. And even worse, pi nu is selected to maximize the q function. This is very bad news if q is a large neural net. We know that if we optimize with respect to the input into a neural net, we can more or less trick it into producing any output. That's the basic idea behind adversarial examples. So if you're allowed to manipulate the inputs however you want, you can trick neural nets. They might be very good neural nets overall, but you can find some crazy input that will get them to produce a crazy output. And we actually see this in practice when we actually run these naive algorithms. We see massive overestimation where we end up with q functions that have values that are much larger than the true q values because of these adversarial examples. So I won't talk about the numerical experiment here, but roughly speaking, you get very, very large overestimation. Okay, so there are many offline RL algorithms that try to address this problem in various ways. And I'll summarize just one method for you guys, because that's what we're going to build on for the experiments I'm going to describe next, but keep in mind there are other solutions as well. But this one is like a fairly simple solution. So the idea is this. If this green curve is your target values and the blue curve is your fit, it's a pretty good fit. The problem is that in the place where it overestimates the most, that's exactly what the max is going to pick up on. So what we're going to do is actually pretty simple, kind of inspired by adversarial training. We're going to find these overestimated points, and we're going to try to push them down. It's a very simple modification to the classic algorithm. So this objective, that's that Bellman error minimization from before, exactly the same as regular Q-learning. And the change is this term up above, which finds a distribution mu that has large Q values and then minimizes those Q values. So push down on the big Q values. Very simple idea. And if you do that, you can correct these defects. There's a little bit more detail that you need to get this right in terms of a practical algorithm, but that's basically the core idea. And this is called conservative Q-learning. It works in practice. It also works in theory. You can actually prove that if you do this right, you can avoid this overestimation problem, which means that you'll actually get a working offline RL method. I'll talk about one example application of this method, but then before getting into all the robotics stuff. So this kind of illustrates also some of this like pre-training fine-tuning ideas that I discussed from before. Atari games. Okay, not the same as space exploration, although there are some Atari games that involve going into space in a very rudimentary way. We're going to take 40 Atari games. So you can imagine this is like the prior knowledge that our space explorer has here on Earth. They got to play 40 Atari games. Not maybe the ideal NASA training program, but okay. And we're going to train a Q function with offline reinforcement learning on all 40 of those Atari games. And the data from those Atari games is not optimal data. The data is essentially just, it's actually like the first chunk of an RL run. So you can think of this as a kind of very mediocre human tapping on keyboards trying to play the game. So it's better than random, but a lot worse than optimal. And we get a pretty good policy for playing these 4 Atari games. This is a comparison to other methods. So the green curve here is decision transformers, if you guys know about that. The pink one, that's the final version of this CQL-based method. And it's an 80 million parameter ResNet, and it does pretty well. So the dotted line is what the average in the data set is, and you can see that it's doing quite a bit better than the average in the data set. But of course, that's not the most interesting thing. The most interesting thing is that now we can train this Q function on lots of Atari games. Can we, send it to another planet and get it to actually leverage that knowledge in some meaningful way? So to do that, we're going to give it a new game and fine-tune from the initialization we got from those 40 Atari games. And we're going to do 2 fine-tuning experiments. This one fine-tunes on offline data for the new game. So you can imagine someone kind of taps on a keyboard in some arbitrary way, gets some mediocre data for a new game, use the initialization from those 40 games, and fine-tune. So here, the pink bar, again, is the method that was pre-trained on all those 40 games. And maybe a reasonable comparison is the orange bar, which is the same exact model, but trained from scratch on that game. So basically, the difference between the pink bar and the orange bar is the pink bar is our Space Explorer was trained on Earth with lots of Earth data. The orange bar, it had to learn from scratch on this alien planet. So clearly there's something pretty good happening here, in some cases much better. Appropriately enough, Space Invaders does pretty well. You can also do online fine-tuning, right? So you can actually throw it into this new game and actually have it learn by interacting on its own. And there it does pretty well too. In some cases, like Freeway and Breakout, of course this is a time-limited test, so it has a fixed number of interactions. The pre-trained model is essentially infinitely better than the model that learns from scratch, because the model that learns from scratch is unable to get a non-zero score in that time. Now, people have used offline RL, and in particular conservative Q-learning, for all sorts of things. I'll talk about some of them here, including robotics and dialogue systems. Folks have used this for things like optimizing click-through rates for mobile notifications. So LinkedIn used it to basically determine a policy for which notifications to push to your phone to avoid extraneous notifications. It's been used in e-commerce and other applications. So this is like a pretty good fit for the kinds of decision-making problems where you can get data, let's say, from customers and things like that. And that's a very practical side of this. But you know, I don't do necessarily very practical things, so I'm going to tell you guys about robots and things like that that are maybe a little further out. So let's talk about how we could start applying offline reinforcement learning to robotics problems. Now, the first thing we need, of course, is we need a data set. Maybe in some distant future, we'll be able to train our robots using data that we scrape from the web, and we're actually working on that right now. But for the time being, let's talk about getting robot data to train our robots. So we want some kind of data set so that when you unpack your robot in your lab, just like the Space Explorer on an alien planet, there's some kind of pre-training data available to that robot so that out of the box it actually has some basic capability. So a big data set of past interactions, maybe from other tasks and other environments, that can prepare it with some body of common sense to tackle new problems that you might want it to address. So you want to kind of bridge this generalization gap between the small amount of data you might have in your new setting and the large amount of data from other environments and other tasks that might get it started. So we collected what we call the bridge data set, which is meant to kind of provide a prototype for how this might work. It's intentionally collected in many settings and for many different tasks, although with the same kind of low-cost robot. This slide is actually out of date. We actually recently released an update, so we're up to 33,000 demonstrations. It turns out that Berkeley students are really good at collecting demonstrations, so the data set is growing very rapidly in 21 different environments now with over 100 tasks. So this is actually outdated. And we're hoping to get it up to 60,000 by the end of the year. And it's really designed to be reusable by other researchers in new domains and for new tasks. And that's what we're going to examine in the experiment. So we're going to pre-train on this bridge data set, and then we're going to try to see, can the robot initialized with offline RL acquire new tasks efficiently? So we call this method pre-training for robots, or PTR, and it's basically conservative Q-learning applied to this bridge data kind of setting. The basic version is actually very simple. We're going to take all the tasks in the bridge data set, and we're going to, just like with the Atari example, we'll train one giant network to do all the tasks. We don't necessarily actually care that much about how well it does all those tasks. We want it to provide a good initialization. So the tasks are just denoted with a one-hot vector that's fed into the Q function. And then we'll reserve the last position in that one-hot vector to be the new task that we're going to fine-tune to. So the last position, that's the alien planet. So we train this on bridge data. And then we take some new task, and we're going to take, in this case, 10 to 20 trials for that new task. Maybe it's like put corn in bowl. It's not a completely unfamiliar task. The task is structurally similar to what the robot has seen, but it has maybe different objects or a slightly different motion or some other different constraint. Or maybe it's in a new environment. And then we'll fine-tune on this new task. The way that we found to work best is we actually, for every batch, we take some fraction of the batch from the bridge data so that we don't forget, and some other fraction from the new task. And that's how we do our fine-tuning with the same exact RL algorithm as the pre-training. And that actually works decently well, so you can learn to put a cucumber in a new pot in a new kitchen using this model pre-trained on bridge data. And one of the interesting things about this is that you can actually compare the performance you get by pre-training on bridge data to the performance that you would get using other computer vision-based representational learning methods. So you can take this same data set and use it in other ways, like train, for example, a masked autoencoder to get visual representations. And that's a very natural point of comparison because that's how people would ordinarily use prior data for pre-training. So the relevant columns to pay attention to here, this is the success rate for PTR on the downstream task. And these two columns, R3M and MAE, these are kind of more computer vision-based representational learning methods that use the same data, but just to extract visual representations. And you can see that these things don't end up doing so well, especially on the harder task, the bottom two. So that suggests that really doing this offline RL pre-training is pulling out more than just visual representations. It's pulling out something that allows the robot to more effectively master this new task.
So does your training have a visual representation or not?
So for the RL example, the model is ResNet 36, and it's just trained end-to-end to perform the task. So the visual representations are extracted as a byproduct of the RL process. And actually on that topic, sorry, ResNet 34. On that topic, this is the scaling laws. You have to have a scaling laws curve in any such paper. As the size of the pre-training of the model in pre-training gets bigger, the performance on the downstream tasks also improves. So that means that there's something kind of good going on, kind of what we expect from large-scale data-driven methods. So the point here is that this is actually bringing in some of that scaling benefit that we see in data-driven AI and combining it with the reinforcement learning methodology. Okay, that's for robotic manipulation. We've done kind of similar things for navigation tasks. I'll go through this pretty briefly, but in navigation, you can do cool things like you can say, well, can you create a data set and model that can generalize in zero shot to entirely new robots? Navigation is a pretty structured problem, so you can sort of imagine that the way you drive a car and the way you drive a small-scale ground robot might be kind of similar. So the setup is that we're going to have actually goal condition policies, so we're going to indicate the destination with an image of the destination. And then we'll collect the data set from all sorts of different ground robots, from large-scale ATVs to little kind of small-scale RC cars, and then try to see if we can generalize it to new robots. And it turns out that actually works. So you can actually get generalization, not just across tasks here, but actually across platforms. So the drone here, now the drone is pretending to be a car. The altitude is just fixed. But other than that, other than the drone pretending to be a car, it actually does generalize in zero shot to the drone from pre-training on a variety of other kinds of mobile robots. So that's pretty cool. And then we can also do this online fine-tuning, the alien planet kind of scenario. So we can pre-train with offline RL on many different robots, and then we could do online fine-tuning on this little small-scale rally car to get it to drive around hallways. This is in Soda Hall, I believe. Some of you might have seen this experiment or might have been annoyed by it if it hit you in the hallway. But the good thing is that you won't be annoyed for long, because with offline RL pre-training, the online stage actually learns in about 10 to 20 minutes, which is actually in my opinion, actually pretty significant, because this is learning from image pixels. So the initialization gives it a lot to go off of. Ordinarily, an experiment like this from image pixels would take hours, but with the appropriate pre-training, it takes tens of minutes. This is an example route. This is actually in Berkeley Way West, and this is the training curve. So y-axis lap time, x-axis total training time. And you can see that the lap time gets to this kind of optimal 40 seconds or so, in this case between 15 and 20 minutes in. And that's about comparable to what an OK human driver does with this car. The OK human driver, in this case, is the grad student doing the research. His driving is kind of about comparable to what the RL algorithm comes up with. Maybe one of you guys, if you're an expert at driving an RC car, could do better, but that's where we're at. All right, so what have we done, and what remains open? Well, we've shown that large quantities of robot data can give us initializations for downstream skills. Offline RL serves as a powerful framework for both pre-training and fine-tuning. And pre-training with offline RL versus kind of the traditional computer vision representation learning seems to really help. Now, there are some limitations. Of course, the skills that I showed are all fairly rudimentary. It's like put an object in a thing, drive around a building. And the data is still narrow, so there's a lot more to be done to go from this to our Space Explorer, but it kind of shows hints that maybe this could actually have some of those properties we want. All right, so I'll briefly touch on two other applications. I'll talk about offline RL for large language models, and then I'll conclude with a brief discussion of human influence. But the idea is going to be very similar. So if we want language models that can interact with humans, let's say that we have something much more interactive than just question answer. We want something that has more of a back and forth. Maybe we're doing like tech support. We can pull in the Ubuntu dialog corpus, for example, and try to train some kind of model that will not just answer questions, but will actually engage with the user, figure out what their problem is, and try to solve their tech support problem. So we'd like to have something that goes in that green box that produces a language model that can talk to a human, ask them questions, diagnose their issue, and then solve their issue. Just copying the humans will not necessarily lead to great performance, because there's some good stuff in there, but okay, this is like some online chat room, so there's also stuff like this person says like, haha, sucker, or this is like, actually, this is not, you're not supposed to do this. This just tells you like, kill your process. It's like, okay, well, that's not going to fix your problem, but it might. It's kind of a nice practical joke. So the data tells us a lot about how humans will respond and what kind of things work and what kind of things don't work, but simply copying the data won't lead to a good solution by itself. So the question is, how do we leverage the patterns in this data to then do better than the average humans in the data set? So I'm running a little low on time, so I'll actually skip over some of this part, and I'll just tell you how it works. Okay, so here is the setup. We really want to make multi-turn dialogue a first-class citizen, so we're going to frame it as a reinforcement learning problem, where the observations are the things that the human says, and the actions are the things that you say. And the state, in that case, is the history, because it's a partially observed problem, so you really need to know the entire history of the dialogue to get your state. Fortunately, large language models are very good at keeping track of history, so that's not really a problem. And the reward is going to be based on the outcome of the dialogue. So this is not like learning from human preferences where we want to produce outcomes that human raters prefer. The dialogue actually has a purpose. This is a benchmark problem where the purpose is to guess which picture the answer has in mind. It's like a game of 20 questions. In the tech support, the purpose might be to actually solve the tech support problem. So instead of learning from human preferences, we're learning from dialogue outcomes. And instead of having a single episode be the utterance that you produce, just the answer, the episode is an entire back and forth. It's a whole dialogue. And crucially, you don't control what the human says, so you have to deal with the uncertainty and the dynamics involved in this multi-turn dialogue. Okay. So I'll skip over this part, and I'll just describe the method to you. So we're going to do this with offline RL, and the method is going to be basically an adaptation of exactly the same technique that we used for robotics to large language models. So it's going to be basically a variant of Q-learning with the same kind of conservatism penalty. And it turns out that it's actually very convenient to instantiate this with a language model if you treat every single token as an action. So instead of treating the entire answer as an action, we'll actually do something seemingly strange and treat every token as an action, because that actually makes the method simpler. So let's say that we're producing our utterance, and we're over here on the word facing. I'm going to pretend like words are tokens. I know they're not, but this will just make it a little easier to visualize. So we're at the word they, we're producing the word facing. A regular language model would just assign a probability to every next token. We're going to assign a Q value to every next token. But the structure of the model will be exactly the same. There will be a number for every token. It's just that now the number means something else. Instead of denoting the probability of that token in the data distribution, it will denote the Q value for accomplishing the desired task. And the loss is a little different, because the loss now requires plugging in the next token, computing that target value, taking the max, that's the max over here, adding the reward, which will be 0 until you get to the end of the conversation, and then setting that as the target. So it's a different loss function that actually depends on the next token, but structurally it's actually a very similar kind of structure to supervised learning, just a different number. And in fact, it's actually illustrative, I think, to compare these. In a language model, you predict the probability of the next token given the previous tokens. In this setup, you predict the probability of success given the new token you're selecting and all the previous tokens. So it's still a probability, it's just normalized in a different way and means something different. That's kind of cool that we still have this token-by-token decoding, we still have a token-by-token loss, but we have a goal-directed learning procedure. Okay. So in practice, if you want to instantiate this, of course, you have to deal with that counterfactual queries problem, which complicates the algorithm somewhat. One practical instantiation described in this paper by Charlie Snell is a method that we call implicit language Q-learning, which actually combines conservative Q-learning with some ideas from another algorithm called IQL. I won't go through this in detail, but it basically has that Bellman error loss in combination with some corrections for the offline part. It trains two models, actually, a proposal model, which is just a supervised fine-tuned model, and the value function. And then it proposes from the proposal model and actually ranks using the value function instead of decoding greedily. And those details make it work a little bit better. I'm not sure how fundamental they are. It could be in future work that will change. But the core of this is that basic Q-learning paradigm. What can it do? Well, here's that 20 questions kind of game. Here the answer has a particular picture in mind, and the questioner is asking them questions so they can guess the picture. If you just maximize for task reward, you can get reasonable questions like, is the man young, is he wearing glasses, etc. You can actually take the same exact data and you can change the reward, and the reward here will depend on the behavior of the answer. You can say, well, I don't want to ask the sort of questions that will lead to uninformative yes or no answers. And the questioner actually understands what that means and starts asking, like, is the person male or female? What is the person wearing, etc. Now, the delicate thing here is that the reward depends on the behavior of the answer. You don't control them, you just control your questions. And you can assign a more detailed penalty that also penalizes uninformative answers, and that also leads to like kind of quantitative questions and things like that. Okay, so the takeaways here: offline RL can learn from humans interacting with other humans. It can be used to train large language models to achieve goals. The evaluations so far are at a smaller scale, so these kind of 20 questions type of tasks, they're really kind of toy evaluation tasks. The big benefit, I think, will come from leveraging more subtle patterns at larger scale, and it remains to be seen how well that works. But I think it's a really promising direction. So since I'm about out of time, what I'll actually do is I'll skip this next section, and I'll make some concluding remarks, and then we can go to the Q&A. But if you're interested in this will be in the slides. You can also do nonverbal human influence. But to wrap up, I just want to leave you off with this slide about the bitter lesson. That I think it's important to remember that if we really want agents that are goal-directed, that have purpose, that can come up with inventive solutions, it'll take more than just learning. Learning is important, and the data is important. But the combination of learning and search, that is a really powerful recipe. Because data without optimization doesn't allow us to solve new problems in new ways, whereas optimization without data is hard to apply to the real world outside of simulators. If we can get both of those things, maybe we can get closer to this Space Explorer robot and actually have it come up with novel solutions to new and unexpected problems. Thank you very much for listening.
Thank you, Sergey. That was a really inspiring talk, and I'm sure that we have lots of questions. We have very few minutes to address them, however. So I invite you to pose your questions succinctly, and we'll take a few minutes for Sergey to respond. We have microphones, and they'll circulate if you want to just hold up your hand if you'd like to pose a question. Hold your hands high. Don't be shy. I see some people like, oh, hey. No?
Regardless about the skill learning, does this occur in other problems we had? Like, for example, tracking the medical things like Parkinson's?
Yeah, so I think conceivably one of the things where I think offline RL could be actually very useful is in medical settings, because one of the things you can do in principle in medical settings is get data of historical kind of treatments, outcomes, and so on. But it's very difficult to do online exploration because you don't want to apply random treatments to patients. So that could be a really interesting application domain. It's not something I've done, but I think it's really promising. I know there's actually a group at MIT that has studied the use of offline RL for kind of hospital decision-making type tasks. Not the kind of things you were alluding to, but more like how do you triage patients.
Other questions? Perhaps, okay.
So I was just curious, so you showed the data set which contained different tasks. I was just wondering, how does that move towards tasks that are not there in the data set? So for example, you showed putting a corn in a bowl, which wasn't probably in the training set. But what if it was, instead of single object grasping, it was multi-object grasping? So how would that translate?
So if you actually want to be able to get the new task to succeed from a very small number of examples, you need some kind of structural similarity. So the general rule here is the same as all other kind of questions about generalizations, that the broader and more representative your data set is, the more variety it can generalize to. Now, of course, the other thing is that you're actually fine-tuning. So in principle, the way that the degradation should happen is that the more unfamiliar the task is, the more experience from that task you'll need to master it. But as in the example with the Atari games, you can actually get an entirely new game. You'll just need more experience to get it right.
One last question.
This is more a philosophical question than a technical one, but in regards to the Ubuntu data set that you showed, you said we want to train our model so that it'll give us a response that's better than the average human. And my question is, why do we bother generating a response that's better than the average human?
Yeah. Well, I mean, it depends on what problem you're trying to solve, right? So if what you want is to get the chatbot to behave in a way that emulates human behavior, I mean, that is exactly what maximum likelihood training is already optimizing for. So sometimes you don't need anything else. But if your goal is to actually solve a particular problem, then presumably you care much more about how well that problem is solved than what people would do in order to solve it. So, arguably the goal of tech support is not to produce behavior that resembles a human tech support agent, but to solve someone's tech support problem. So it's just a matter of what problem you want to solve.
Thank you. So I imagine Professor Levine might have a few more minutes afterward if you want to come up and have a chat with him. But I really thank you for joining us here in person, and come back next week. We'll see you then.